Q-learning. So we've talked about supervised learning. Decision trees are just one example of supervised learning. Ensembles are a better example of supervised learning. And the idea of supervised learning is you want to build a model of the universe. You have data and you want to know if this, then that, right? Okay. Now we're going to move to a different kind of learning called reinforcement learning. What is the difference? Well, the first difference is purpose. And I don't want to suggest that there's any true purpose for math, just that their overall intent seems to be that supervised learning is modeling, meaning you're trying to build understanding of the universe based on data, right? Data to knowledge, something like that. Whereas the purpose of reinforcement learning is decision making. So we're moving back over to the other side, the more AI side of the AI tree. Let's see, supervision. The idea in supervised learning, we call them labels. The idea of a label is that for every sample we get of inputs, we have a corresponding thing we're trying to predict. The label is the color, the number, it's the thing you're interested in. It's an instance of knowledge. In reinforcement learning, you get rewards or punishments, which is more formally just called reinforcement. So the example here is a mouse pushes a button. One's red and one's blue. Every time it pushes the blue button, we shock the mouse. Every time it pushes the red button, we give it cheese. What's the mouse going to do?
Smash that blue button.
Yeah, he'll smash the one that gives him cheese and not the one that gets him electrocuted. Point of reinforcement is to reward or punish good or bad behavior. The point of labels are to indicate what truth goes with what observations. You see the difference? And yet, do you see the similarities? Supervised learning and reinforcement learning are very similar. Both of them require some concept of a teacher or an oracle or something that's going to provide labels or reinforcement. And both of them are going to improve over time, well, if they can, or improve with more data, I guess you could say. And the difference is in reinforcement learning, we're just trying to figure out what to do as opposed to figure out what to believe or what to know or how to understand the universe. We're going to use an approach called Q-learning. And here's some pseudocode. And here's the big equation that's really what the whole thing's about. And this is what I need to talk you through, is make sure you understand this equation. I think the best way to do that is, let's open a grid and do an example of reinforcement learning is often taught with grid worlds. I don't want you to think that the universe has to be a grid or that reinforcement learning only works with grids or that there's anything about grids. Why do we do grid worlds? Because they're really easy to comprehend and understand, but it's really important to me that you know that this is just a metaphor for, hey, we could take this into the real world. Let's suppose you are here, you're a stick figure, a really badly drawn stick figure, and you start here and you're trying to go save the princess, who of course is wearing a dress and lives in that square. But there's a Bowser right here. Pretend that looks like Bowser. And he's bad, and if you touch him, you will die. In fact, let's turn you in. Let's make you red so you can be Mario. Red means Mario. Purple means Princess Peach. And your choices are you can go up, right, down, or left. Obviously, you shouldn't go right, up. Oh no, blah, you die. Bowser ate you. You should go around Bowser and get the Princess Peach. But to further complexify it for right now, what if there are multiple alligator Bowser guys? Yeah, it is basically a breadth first search problem and could very well be solved that way. I'm picking the simplest problem I can possibly imagine for reinforcement learning so that we can show you how it works, and then we'll show you what it can do that breadth first search can't do. You are here, you want to go to there, that would be the optimal policy. Okay, how would you solve this given what you know so far? Breadth first search, right? You'd basically, or A star, that would be a better option. you'd kind of search out in some type of a frontier until your frontier worms its way up here and into there. And as soon as you find the goal, you backtrack the path and get it back to the start, and then won't undo my history anymore. Here's what we're going to do in reinforcement learning that's rather different. In breadth first search, we usually start at the starting point and look for the goal. Let's do it backwards, and let's give a reward or penalty. So let's suppose saving Princess Peach is worth 100 points. Okay, let's suppose touching a Bowser is worth negative infinity points, which we'll represent in computers with some finite number. Let's just say negative 5. Suppose we put a 0 in every other cell, meaning there's no value for being in that cell. And suppose we overlay on top of this thing a map that's going to indicate the value of being in every position. What do you think the value of being right here is? Well, immediately you get 0 value for being right there. But in the long term, we know that if being right there is a good thing because, hey, in the next step we can get 100 points. Let's suppose we say time is worth 1 point, just because it's something to do. Then would you agree with me that being here has a value of 99? Because we're going to lose 1 point in time and gain 100 points in score. So all of these cells are worth 99. Well, if that's true, what's the value of being right here?
98.
Surely it's 98, right? And so is this, and so is this. 98, and so is this. But what's the value of being right here? Yeah, it's 98 minus your 5 points that you're going to have to take. So what's that, a 93? 92?
Yeah, because it would be...
Oh yeah, you're right. Let's go with 92, because 1 hit for the move, 5 hits for touching Bowser, but hey, we're still anticipating getting that 100 points. Well, then that means this one's worth 91, this is worth 90, 89, 88, 87, 86, 85, 84, and the value of playing this game is at least 83, right?
Okay.
But is it exactly 83?
Maybe.
Maybe we'd have to try all possible paths. How could we do it? Well, suppose we write a double for loop that visits every cell in the entire map, and at every cell we propagate 1 step adjacent to it in all possible directions, and then we repeat that in a loop. So now it's order n by m by number of iterations, order n cubed operation. Very expensive, right? But we could, and every time we did it, value would propagate a little bit, and the negative values here would propagate out, and the positive values of the rewards would propagate out, and eventually it would converge to some value of every cell, right? If we had the value of every single cell, what would you do? Well, we've turned a complex problem into a greedy optimization problem. Now we could simply follow the trail of the best breadcrumbs until we got to our goal. You see that? Okay, well, here's a question. What happens if we walk around this thing? That makes this worth 97. Oops. I'm doing red to... By the way, we got to keep straight the difference between rewards and value. I'm using red here to indicate the value of the cell, and I'm using black to indicate the reward that is given to you when you land on that cell. You got that straight?
Yes.
Okay. So the value of this cell, 95, 94, 93, 92, 91, 90, 89, 88, 87, 86, 85, 84, which means this one could be an 83. Which value should that cell take? Should it be an 83 or an 84?
83.
You say 84? I heard an 83. Why is...
Oh, wait.
What should we do? Do you see what this has to do with utility theory? In utility theory, when you have a decision to make, the value is the better decision. Why? Because in the future, you'll do the best thing. You can rely on your own future intelligence. Therefore, I claim the value of going into this cell should be 84 and not an 83. Why? Because if I go there, what am I going to do? I'm going to go up. I'm not going to go to the right. Why? Because it's suboptimal. Now, I bet you when you saw this game, you thought to yourself, the right answer was going to be go right, go up, go over, and get Princess Peach, right? Because you don't want to go through one of the Bowser squares. Ha-ha, I got you. Because it turns out the more optimal answer is to go up to here, take the hit, and come down and win the game. And it turns out that if these values correctly represent reality, again, there's the hard part. Matching your priorities with reality is always a difficult thing. But if those numbers are defined as the truth, it turns out that we can say the better choice at this point is to go up, plow through Bowser, take the hit, and win the game, and that's better than just searching around. Do you see how this is actually is more powerful than search algorithms?
Yeah.
Because this approach works with multiple goals of differing values. Maybe that princess has 100 beauty, and this one only has 32 beauty. Okay, that makes me feel awful even talking about such a thing. But suppose that were the case, and let's not go for beauty. Let's go for, well, no, that's even worse. Desirability units. Nothing I can say will make this right. Pretend she's not a princess, pretend they're treasure chests, and this treasure chest has 100 gold doubloons in it, and this one has 30 gold doubloons. Which one should you go for? Well, ultimately, this whole thing is just a big, complex utility theory problem, is it not? But here are some factors. We need to put value on how much our time is worth. We need to put value on how much the goals are worth and the penalties and the actions. And if we can do that, if we can assign values to all that, it turns out we can propagate through this whole tree. And these values end up being the thing we have learned from our reinforcement. So that 100 points for saving the princess, that's reinforcement. These -5 points for fighting Bowser, that's reinforcement. These red numbers that I put here, the value I've assigned to each state, that's utility. That's the value I assigned to being in that state. And by spreading out the rewards through decisions and probabilities and whatever else comes up, we're kind of using an approach it's a convergence approach to doing utility theory. And so what we're going to do in Q-learning is make a loop. This is pseudocode for one iteration. There will be a big, massive main loop around this whole thing. And in this loop, we're going to propagate the values around. And by the time the values converge, they represent optimal utilities, which tell you what decision to make. And then if you can apply this to a grid world, could you apply it to, say, a robot washing dishes?
Lose 5 points?
Yeah, every time the robot breaks a plate, what do? You penalize it. You just give it a bad job. And when the dishes are nicely washed, you say good job. And so now the robot's going to go in and start out running through this space. And what are the x and y axes in the case of a robot? Well, maybe the x-axis is the rotational force on its wrist, and the y-axis is the rotational, or the joint force on its elbow. And you see we're going to need more than just 2 dimensions, right? We might have another dimension that's the force on its shoulder muscle, and another dimension that's the clamp force on its hand. And if we had, say, a 12-dimensional hypercube full of values, we could propagate values through it, and by the time we were done and had converged, this robot would optimally know how to wash dishes. It could go in there and move its joints around, which is analogous with moving Mario right and left and up and down. And it's going to navigate through this space to getting the job done and earning a lot of rewards while avoiding badnesses like stepping on the cat and breaking dishes and whatever else you don't want your robot to do. And so it's kind of like the very first problem we did in this class. Remember, we were moving the pieces around to solve this Professor Layton puzzle? But in hyperdimensional space, navigating around a maze is kind of the same problem as washing the dishes, is it not? I mean, the problem involves joints and motions and actions that you're going to choose to control your robot body to pick up the dish without breaking it or killing the cat and without stabbing yourself with a knife. And yet, in the end, the goal is some state where all the dishes are neatly stacked. And there's not just one goal, there's probably lots of them. But you see how this is a nice general solution for pretty much doing anything? Kind of. And that's why reinforcement learning is cool, so that's why we're going to delve into it a little bit. Yeah, this is an example of pretty much optimal output. And your results won't look quite this nice. I made this by hand in a hurry in a text editor, not with reinforcement learning. So yours will be like this, but noisier. And I'm just kind of saying, hey, anything even remotely kind of like this suggests you've done a correct implementation. So yeah, this is kind of your goal. What this actually is a policy. And let's talk about what a policy is. Wouldn't it be really nice if you could feed state into a magical learning machine, and what would come out of state is the action that you should perform? This is what's called a policy function, or just a policy. State represents everything you know about the universe. So you've already applied all of your machine learning and your modeling to understand the world and try to figure out what state you're in and what things mean. Given that you have all this information that you've produced and digested, this is the state of the world, and this is what you should do. If you could learn a function like this, then that would be enough to control your robot. Do you agree? Or solve whatever problem you have. This is kind of the goal of AI, is to produce a policy. A policy is just some model that tells us, in this condition, this is what you should do. Kind of the goal of machine learning is, given a bunch of observations, figure out what your state is. So you put those two pieces together, and you've got the full artificial brain. This is a representation of your policy. In every state in this board, because it's a grid world, there's only two dimensions, x and y. In every state, we're going to tell you what to do, and those are go left, right, up, or down. I've represented these with greater thans, less thans, the letter V, and the caret symbol. Just because then you can code this up with a simple console-based app, and we don't have to mess with graphics, and that makes life super easy. Okay. Hash symbol represents a wall that you can't pass through. The letter S is where you start, and the letter G is your goal. And this is pretty much the dumbest, simplest problem you could possibly apply Q-learning to. But hey, there's only so much time left in the semester, so we'll build a dishwashing, robotic, awesome Q-learner over the holidays when you're not being graded. Can you see that if you started in the start state and followed the arrows, you'd basically end up at the goal? Okay. If you achieve just that, then it worked. And if it can also say, hey, if you were to be plunked at some random place in the universe, and it would probably get you to the goal or something near it, that's good too. And if most places lead to the goal, that's a really good policy. So this is what we're going to try to do in this code. In order to do it, you'll implement this pseudocode and do try to understand it. I'm going to talk you through what it means and how exactly it works, but try to understand it a little bit so you get more out of that lecture. And the big centerpiece of Q-learning is this equation. This is what I really want you to understand. This is the kind of stuff I'm going to test you about. So